Sorry guys, again, I ran out of space on my camera to record the whole computation that I was performing on the Bootstrap Circuit design for the common emitter amplifier we designed. So let's go ahead and continue the actual result of the computation, and we'll do the actual measurement in this video. So as I showed you, the equation 1 for the node Vx is this. This is for the Vy node, and this is for the output node. And after we solve, use the solve command in the Maxima software, we're gonna get this expression, this long messy expression. So if we now isolate this equation, which relates the output voltage with the input voltage, you can see Vi and Vo. So this one is the transfer function. So if we isolate that and we divide it by Vi, then we're going to get the transfer function of the circuit. This is the Bootstrap circuit that we designed on my previous video. And if we plug in all our values, like the R3, RE, RLC, which is a parallel combination of RL and RRC, R12 parallel combination of R1 and R2 for the biasing section, small base emitter dynamic resistance of 52 ohms, and the source resistance, we put all of them in alpha, beta, beta plus 1, we're taking beta as 100. We're gonna get our new voltage gain of minus 19.32. Our previous non-bootstrapped common emitter amplifier only had minus 15.7 voltage gain because of the input impedance of that amplifier was loading. So loading the source, and because of that, then the voltage gain also decreased. But now we're getting a good voltage gain. That's good. This is one thing we can remember. So we'll verify this by measuring the circuit I built. And let's go ahead and do a computation for the input impedance. How much does the input impedance increase? Remember our input impedance from previous video that we calculated for the non-bootstrapped common emitter amplifier was about 2.85 kilo ohms. We even measured that, which practically agreed spot on. So now, does this circuit, which we included the network, the feedback, the positive feedback network, does it help in input impedance? Let's take a look. So we're going to do similar equation, but now we're going to substitute Ix, which is our input current, so which is basically this term here, which is Rs, this term is Ix. So if we include that into our new equation E6, which is basically this. So if I show you the actual equation from my paper that I wrote, so this is basically what I'm talking about, Ix here. I showed you in previous video, but here to recap, I'm showing you again. So as you can see, that's Ix. So Ix comes into the node here, so it's going to be negative. So, and that's going to replace the voltage Vx minus Vi divided, sorry, the current Vx minus Vi divided by Rs, which is basically this one. So this one is going to replace it. So this one is going to be minus Ix. That's what I'm writing on that software, the equation that I showed you. So minus Ix and this term and this whole term here, this 3 equation. Now this replaced by Ix. We're trying to solve our input impedance. So let's go ahead and solve it on the software. So there it is. So I'm substituting that with minus Ix, same equation after. So now we get this. Now we're going to solve the equation that we did and the 2 equations above, E2 and E3. We're going to solve it for the intermediate voltage Vx, the output voltage, and the intermediate voltage Vy. Now, right now though, because we want to calculate the input impedance of the amplifier, which is Vx divided by Ix, we're gonna solve for Vx here. We're interested in Vx here. We're gonna get this expression, and as you can see, it has Ix as a term. So if we factor Ix and divide it to this side, we're gonna get Vx divided by Ix, which is our input impedance. So our input impedance expression is this. And as above, if we put in all the values that we designed, like all our alpha, which is beta, divided by beta plus 1 and all the values, we're going to get our new improved input impedance of the common emitter amplifier, which is bootstrapped by the capacitor 10 microfarads and the 6.8K isolating resistor. We're going to get our new input impedance of about 39.78. So let's call it 40K. So as you can see, the positive feedback that we used is helping us to increase our input impedance from 2.85 kilo ohms to 40 kilo ohms. So that's a lot of increase in input impedance, and that is what positive feedback can do. Normally, positive feedback, you don't use it in circuits because it tends to create an oscillations, right? Because the feedback that you're using is in phase with the input. It tends to create basically oscillations. So if you want to create a good oscillator, then you normally use positive feedback. So, but in this case, the positive feedback works into our advantage. It doesn't create an oscillator when we're designing this amplifier, and because the gain, the common emitter gain. So if I show you the circuit again to be absolutely sure. Yeah, the circuit is here. So if we take a look, we're taking the emitter, we're taking the feedback from the emitter, and remember, because AE, which is our gain, our emitter follower gain is always less than 1, but very close to 1, then the feedback signal is not going to create an oscillator because of that, because the gain is less than 1. There is for a condition to create an oscillator, there's two conditions you have to meet. One is the gain condition and the other one is the phase condition. But in this case, the gain condition is less than 1, so we're not going to create an oscillator. So because of that, it works into our advantage in this case. So rarely do you see in amplifier circuit design positive feedback. Normally you use negative feedback to make the amplifier behave nicely, and so in this case we're using positive feedback to our advantage. So normally we don't use that when you design amplifiers, but this is a side note. So now what we'll do is we'll show you the circuit that I modified and see if the theory that we just calculated matches the actual circuit. So let's go ahead and do a few measurements. First thing first, let's take a look at the voltage gain of the circuit with the bootstrapped circuit. I've modified it, so as you can see now, the voltage gain of the amplifier is going to be the output voltage, which I'm measuring channel 2. That's going to be 3.94 volts, and I'm injecting 202 millivolts, so 0.202. Now our voltage gain is going to be, if we calculate it here, it's going to be 19.6. So it's going to be negative. So our new voltage gain of the bootstrapped circuit is going to be minus 19.6. So as you can see, because we're not loading the circuit that much, because of this bootstrap section, our voltage gain increased from minus 15.7 to that. So as you can see, we have increased our voltage gain because of the bootstrap section, because we're not loading our source anymore that much, because our input impedance is huge now. And we'll take a look how much that input impedance is measured. The calculated value was, remember, 39 kilo ohms, but we have calculated that at beta equals 100. So the transistor parameter plays quite a role in this, but we'll take a look at that. We'll see what we get. First thing first, let's take a look if putting the R3, the 6.8K, upsets our biasing voltages. Remember, our biasing voltage here was about 1.63 volts. So let's see what we get the voltage here. So let's do the measurements. First thing first, let's take a look at the modified circuit. So now the modified circuit looks like this. Now I have put in the feedback capacitor from the emitter back into the the feedback resistor R3, and the small 6.8K resistor I put in, see if I can put it on the shot, is right here. This is the junction where all of three of them meet. So basically where they all meet is this point here, and I just showed you that one, and I showed you this. CF we calculated it to be 10 microfarads, so anything above 10 is good. So I didn't have 10 microfarads, so I put in about I think this one is 470 micro. I know it's big, but anything above 10 micro will do. Transistor as usual is here. So now let's do the bias measurements. Remember before, if we measure the base, which I'm gonna show you here, this is the base is around as you can see, it's 1.6 now, and before it was 1.63. so that's the base voltage here. Because now the reason is because at R3, so we measured, I just measured here, it's 1.61. so you can see that if I go measure this point here again, so which would be right here, so this is where they all meet. So if I show you that, that's around 1.6275 volts. So as you can see, the DC voltage drop across R3 is minimal because I put it in a reasonable small amount of value, right? I don't want to upset my biasing, my DC biasing, because if you put a large resistor here, the current that goes through it is gonna drop a lot of the voltage here, so our biasing won't be good. We're not gonna create a stiff biasing, as I said before. Okay, so the DC measurement looks good. So now, and we have also seen our voltage gain, which has increased just exactly to what we calculated, was minus 19.3. So it's very close to that. We got minus 19.6. Now let's take a look what's our input impedance. So as you can see, I'm injecting again here 1 kilohertz at 0.1 volts peak to peak, but because this has a 50 ohm output impedance, the voltage that we're going to read at the base will be double of that, because this is with respect, if we attached 50 ohms at the output of this guy to ground, we would have read exactly 0.1, but right now, as you can see, we're inputting 202, so double of that basically. So notice that. So in our calculation, we'll use this guy because our input impedance is high now, right? It's not 50 ohms, so it's higher, so it's going to be double the amount that we're injecting. So as you can see, that's our input impedance peak to peak. The RMS is then going to be 70 because we divide this by 2 and divide it by square root of 2. We're going to get the RMS input voltage of 70.6 millivolts. What is the current? Remember, our current input, what did we read before? We read 23 around, I measured it here if you remember from previous video, it was around 23 microamps. And we did a calculation, our input was 67.6. We did a calculation, we got exactly the same as the calculated input impedance. What do we get now? Take a look. We are putting in 1.3. See if I can focus this. 1.3 or 1.13 microamps at voltage of 70.8. So our input, our new Zin, so I'm going to calculate it here, is we're putting in 70.8 millivolts divided by 1.12 microamps. So what do we get here? Our new Zin. Our new Zin is our improved Zin, right? Let's get that closer so you can see better. So our input voltage now, you can see that it's not getting loaded. Before we were reading 67.6 millivolts, now we're reading 17.8. It's not getting loaded, and our current decreased. So let's do this calculation quick. So if we do this calculation, it's going to be 70.8 millivolts. So that's shot here. 63K. So our improved Bootstrap circuit has a new input impedance of 60.